Okay, now we're talking about work. Our definition of work in physics is we physically have to move an object for it to happen. If there's no motion, there's no work being done. And when we move object, what we're really doing is transferring energy to it. And that's kind of important. So when I pick an object up, I'm transferring energy to it. I'm giving it potential energy. When I slide an object across the ground, I'm giving it kinetic energy. So that's important. We'll tie that together later. Now, the rate at which you do work, is power. And power is simply work divided by time. More on that later, but I'll just throw it in now. So power is work divided by time. Key thing to understand, if there's no movement, there's no work. No move equals no work. So in other words, if I push on a wall, I'm not doing any work by pushing on that wall. It's not going to happen. To be honest with you, you're applying a force, and the force must cause a displacement. If the force does not cause the displacement, there's no work being done. Now, the formula is fairly straightforward. W is equal to F times D, force times displacement. Units wise, we can take a look at it. We know that force is going to be measured in newtons and distance is measured in meters, so therefore it's joule. That's the same unit we will encounter when we're talking about energy. Work and energy go together. Now, there is one caveat to this. The force must be in the direction of motion. So in other words, if I'm applying additional force that's not helping it move, that's not doing any work. So if I pull something in an angle like this with some F, and this is theta, it's only the part of F that points in that direction, which is going to be this. That's the part that points in that direction. It's only the red part that does the work on it. So generally, when something's sliding along the floor, the work is going to be F times D times the cosine of theta. F cosine of theta is the amount of force that's actually in the direction of motion. Since cosine of theta doesn't have any units on it, it doesn't change unit-wise anything that's being done. So let's take a look at that. Key thing that I'll throw in here is the fact that if you have something moving in a circle, let's say I have a discus thrower throwing a discus. And if you have a discus thrower, and this is the top view, that's his body, that's his head, here's his arm like this. It's got the discus cradled in her hand or his hand like that, and they're spinning around in circles like this. There's a tension being applied inward on the arm. The velocity and also the instantaneous displacement is tangent to the circle. So therefore, in this case, there's no work being done, because the F and the D are perpendicular to each other. So if F and D are perpendicular, that's no work. When the International Space Station is going around the Earth, gravity is not doing any work on the International Space Station. Okay. Now, let's do an example problem. Let's, I don't know, let's pull a wagon. Let's pull the wagon at, let's say 20 degrees, and let's pull it with a force of 40 newtons. We got a kid pulling a wagon home. That's some artwork there, baby. And what I want to do is he's going to pull it at a distance of 10 meters. If he pulls it at a distance of 10 meters, I want to know how much work he did pulling the wagon home. Well, work is going to equal to F times D times the cosine of theta. So if we go F times D times the cosine of theta, Again, it's only this part, so it's going to be less than 40 newtons that's actually doing the work. So 40 newtons times the distance of 10 meters times the cosine of 20 degrees. Newton meters times 0.41, which is a cosine of 20 degrees, so therefore I'm going to get 164 joules of work when he does it. Again, he wasted part of the force that he applied. Ideally, he'd want to pull it perfectly horizontal. That's just not always practical. It is, though, when you're pushing something. If you're in a car, let's say you have a car that runs out of gas and you need to push it, you have a choice. You can push it that way, you can push it that way, you can push it that way. Which would be the best choice for maximum effort, for doing us the best? Obviously A. A, because now all the F is parallel to D, so therefore you're going to maximize the amount of energy you have. Okay, let's take a look at another way this can be done, and that's graphically. Because I can easily have a graph, and this is something easily can be created in a laboratory setting or in a real world setting, of F versus D, and I can have any type of shape I want. I don't know, something like that. You're not going to see anything like that in physics. In everyday life, there may be some examples of that. But here's the key thing. Anytime I have a graph, does the slope tell me anything? Does the area tell me anything? That's the first thing I want to think of. Now, there's two ways to do it. You can do it by simply using the units, or you can do it by using the variables. Let's do it with the units first, or excuse me, the variables first. Slope is going to be rise over run, which is F over D. That doesn't ring a bell. I don't think I've seen that before, so I don't think that's right. Area is equal to F times D. Hey, that's equal to work. So the work done would be the area under the curve. So if they ask the work done between unit 1 and unit 2, it would be that area. That's a little sticky, so they're not going to give you something that looks that ugly. Now, if we do it with units, we know that force is going to be in newtons and distance is going to be in meters. My slope is going to be, well, newtons divided by meters. It's not something I've seen before. The area is going to equal newtons times meters, and of course we know that that's work. Anytime you have a graph, you can do that. Does the slope tell you something? Does the area tell you something? Okay, let's do a sample problem. Okay, so I have something like that. I have a variable force that occurs for 2 meters, and then after that it's a constant force. And what I want to figure out is how much work is done for the whole 6 seconds. Now, to calculate that, what I'm going to do is break it up into areas that I can handle. I can handle that, I can handle that. This is going to be 1/2 base times height, 1/2 2 meters times 4 newtons, 8, that's 4 joules of work. If I know how much work we did right there, we also know how much energy it gained, and more on that later. Now, in the next case, I'm going to have a rectangle, which is simply going to be 4 meters times 4 newtons, and this is 8 joules. So the total amount of work I did was 12 joules. The total amount of work I did was 12 joules. The amount of energy the object gained was 12 joules. Now, here's a key thing to understand. Work is a scalar quantity. Even though it's two vectors that create it, it's a scalar quantity because it's something called a dot product, which you'll see later in math. So if you go through there, realize that it's a scalar quantity. and that's kind of important. You just add them up. I can have negative values. If I talk work done by gravity, what's going to happen now is the force may be acting down, and if the displacement is up, I could have a negative value of that, and they're going to be equal. In other words, when I climb a flight of stairs, I have done work, I have gained energy. If I consider up to be positive, that would be a negative amount of total work that I did. But more on that later. Thank you. Hope to help.